So previously, given a compact Riemann surface X, we have given one way to view the holomorphic maps from X to the projective space. Namely, we could identify them with tuples of meromorphic functions on X. In this video, we're gonna give an alternative, more geometric way to think about this. Namely, in terms of linear systems. Alright, so first let's motivate this viewpoint. So remember that every holomorphic map from X to the projective space is going to correspond to some tuple Fi. So now our question is, how do we view this Fi geometrically? Now the Fi are meromorphic functions on a compact Riemann surface. And our compact Riemann surface, the special thing about compact Riemann surface is that every meromorphic function is uniquely determined by its zero end poles. So maybe we can think of Fi in terms of its divisor. So maybe we can associate to the map F0 Fn, we can associate to that the set of divisor div F0 and div Fn, because we can recover the Fi from this. However, the problem here is this association is not well defined because the map phi could also be represented by another tuple, right? And so if we choose another tuple, then the corresponding set of divisors will be different. So let us try to refine this a bit. We still want to associate to the map phi a collection of divisors to be able to think about it geometrically, right? But we will want to rephrase the choice of the divisors. Well, to build some intuition for this, let's look at a concrete example of the case of a map to the affine space instead of projective space. And here, for convenience, I will assume that X is affine, lies inside the plane, but that's not really necessary. So let phi be a map from X to the affine space given by the functions f1, f2, f3 with this coordinate. So these are actually holomorphic functions. In this case, because up to a change of coordinates, phi has only one representation here, so we could associate to phi this collection of divisor. But we want to recharacterize this collection of divisors in a way that will actually allow us to generalize this to the case of projective space, map to projective space, in which we might not have just one representation of phi. Right? We might not have, that will not correspond to just one tuple. So just for practice, let's have a look and see what these divisors are. So what is div F1 as a divisor on X? Well, a common mistake is to think that div F1 must be this hyperbola, right? But divisor of F1 viewer is the divisor on X must consist of point on X, so that must be the intersection of this hyperbola with X. So these 2 points are the divisor of F1, so the zeros of F1, and then similarly now we can draw the zeros of F2. So this is div F2, and then finally div F3, right? So okay, so I have color coded them as a hint. So do you see now how we can rephrase this divisor? So observe then div Fi is just gonna be the pullback of the divisor of xi, where xi are the coordinate of the codomain on C3. Why? Because, see, for example, to find what are the zeros of F1, to find div F1, what did we do? We just set this first coordinate equal to 0, right? We're setting this first coordinate equals to 0, and that basically what we are doing is that we are taking this composition and set it to 0. So the zeros of Fi are just the zeros of xi composed with phi, because that is what Fi is. By definition, Fi is xi composed with phi. In the Fn case, we have very conveniently that the Fi are just pullback of the xi, and the xi are coordinate function, meromorphic functions. In the projective case, these aren't functions. The xi are not functions, so we can't say that the Fi is going to be pullback, but the pullbacks of zero set make sense. So we can still look at the pullback of the divisor of the coordinate functions. So now coming back to the projective case, let's say we have a holomorphic map phi from x to Pn. We fix some homogeneous coordinate x0, xn on Pn. Intuitively, the picture is as follows. Each of the xi is gonna cut out some hyperplane, right? And then we are interested in the pullbacks of those hyperplanes under phi. So let's say this potato-like figure is x, right? And then we want to look at this green part, the pullback of the hyperplane xi inside x. In other words, we want to look at the collection of the following collection of divisors, phi star of the div xi. But there's a problem here. This is not canonical because this depends on the choice of a coordinate on Pn, right? So to account for all the possible coordinate change, we want to look at not just the pullbacks of the divisor of these specific coordinate functions, but the pullbacks of all hyperplanes, all possible divisors of linear forms. We might also write this by phi star h, where h is the hyperplane cut out by the linear form L. Thus, given a map from X to the projective space, we have associated to it a collection of divisors. Right, these are going to be pullbacks of hyperplanes in Pn. Now the question then is, which collection of divisors arise this way? The answer turns out to be the collection of divisors that are base point free linear systems. So let's review what these things mean.